Okay, let's unpack this. Think about programming for a second. At its very heart, one of the most fundamental building blocks is the if-then statement, right?
Absolutely fundamental, yeah.
If this condition is true, then do that. Simple, elegant, and, well, it's absolutely everywhere. It powers everything from your smartphone to, I don't know, complex scientific simulations.
Totally.
But what happens when you try to bring that seemingly straightforward logic into the wild, wonderful, and frankly, incredibly complex world of quantum computing?
Yeah, it gets tricky fast.
Right.
And that's precisely where one of the biggest challenges in quantum programming really pops up. Our quantum hardware today is still, quite limited.
Exactly.
And making those conditional operations work efficiently in the quantum realm without overwhelming the system or, crucially, collapsing those delicate quantum states, well, that's a huge hurdle.
So just to be crystal clear, the challenge is holding on to those fragile quantum properties, the superposition, the entanglement, while doing something as basic, really, as classical if-then logic.
Exactly. You need the logic, but you can't destroy the quantumness to get it.
Okay. So our deep dive today is all about a fascinating new approach called efficient quantum control via automatic control skips. And our mission really is to uncover how this innovative method is making quantum programming far more practical and resource efficient.
Which is desperately needed.
It feels like a genuinely exciting step forward because it seems to significantly reduce circuit complexity without sacrificing correctness. It's tackling one of those core challenges head on.
It's absolutely crucial. I mean, conditional statements that if condition do something, logic.
Right.
They're fundamental to any complex algorithm.
Right.
You simply can't build sophisticated programs without them, whether you're dealing with classical bits or quantum qubits.
Yeah, it makes total sense that you'd need them for quantum algorithms too. But here's the quantum conundrum, as you put it. In classical computing, to check a condition, you just measure it, right? See if it's 0 or 1.
Yep, simple check.
But in the quantum world, that measurement, well, it collapses the wave function.
Oh, God.
And that's one of the biggest advantages of quantum computing in the first place. You lose that incredibly powerful superposed state if you just measure too early.
Precisely. You kill the magic, so to speak. So the traditional solution, the way we've been getting around this, is to use what we call control gates.
Control gates. Okay.
The CX gate, or controlled NOT, is probably the best known example.
Right, I've heard of that one.
It basically allows operations to be conditioned on the state of another qubit without forcing an immediate measurement. It preserves the superposition.
Okay, so that sounds like a necessary workaround for conditional logic in quantum.
Right.
But what are the downsides? You hinted they're not perfect. Are they as easy as classical if-thens?
Oh, far from simple. They absolutely are costly. Very costly.
How so?
Well, for one, they're inherently multi-qubit gates. They have to act on the qubit holding the condition in the qubit you want to operate on.
Okay, so more complex interactions.
Exactly. More complex interactions mean they're harder to implement physically, and generally they exhibit lower fidelities.
Lower fidelities.
Yeah.
Meaning more errors.
A higher chance of error when you actually run them, yes. Which makes your whole circuit more complex and much more fragile. And what's more, many controlled versions of, more complicated gates aren't even native operations on current quantum hardware.
So you can't just tell a machine, do a controlled Hadamard or something.
Not directly, no. You often end up having to decompose them, break them down into sequences of simpler native gates.
Okay, I see where this is going.
Yeah, that just balloons your gate counts, the total number of operations.
Yeah.
And it increases the circuit depth, how many steps are needed in sequence.
Which makes it take longer and introduces more chances for errors along the way.
Precisely. All of this just degrades the overall quality and reliability of your quantum computation. It adds noise, it adds time.
So essentially, these control gates, which you need for logic, they become a kind of fundamental limiting factor. They limit the complexity, the size of algorithms we can actually run today.
That's it.
It sounds almost like a catch-22 situation. You need them to build anything interesting. But using them quickly makes your algorithm impractical on current machines.
You've hit on it exactly. They are indispensable, but their high cost in errors, in resources, it really highlights the desperate need for a more efficient approach.
It's like needing a super fast car, but the only ones available just guzzle fuel at an absurd rate, making long trips impossible.
That's a pretty good analogy, actually.
Okay, so that sets the stage for the problem. But now, here's where we get to the aha moment,
I see.
right?
The good news.
The good news is, as recent discoveries show, it's often possible to, well, to just skip the execution of some of these control operations.
Right. You don't always need them.
You don't always need them. It's a bit like realizing you don't need to put every single item on a factory conveyor belt through the X-ray machine if some are obviously, say, made of wood.
Exactly. That's the core insight. Let's take a specific example, like the one from the source material. Imagine you have a block of code, a sequence of quantum operations. Let's call them A, B, C, D, E.
Okay, A through E.
Now, the straightforward, sort of naive implementation, if you wanted this whole block to be conditional, would be to apply a controlled A, then a controlled B, controlled C, controlled D, controlled E, every single one controlled.
Makes sense. If condition do A, if condition do B, and so on.
But the remarkable part, the aha, is that under certain conditions, you can actually skip controlling some of them without altering the final outcome of the circuit.
Really? How does that work?
So for instance, maybe you could apply a controlled A, then a controlled B, but then just an uncontrolled C.
Just plain C.
Just plain C. Then maybe a controlled D, and finally an uncontrolled E.
Huh. So you skip the control on C and E?
Exactly. And the amazing thing is, the overall result of that block, A, B, C, D, E, can still be exactly what you intended, even with those skips.
Wow. And the benefit is obvious, right?
Absolutely. By not controlling operations C and E in that example, you immediately reduce the number of those resource-intensive, error-prone control gates in your circuit.
Fewer gates, less depth, fewer errors.
It can significantly improve the circuit's quality and performance, makes it much more feasible to run on the noisy hardware we have today.
That feels like, well, a huge deal. So if these skips are so beneficial, is this a brand new idea, or have people sort of known about this?
That's an excellent question. And the answer is kind of both. Control skips have indeed been used before. People have found ways to optimize specific algorithms this way.
Okay, so it's not totally out of the blue.
No, but the critical piece to understand is that finding these patterns was previously done manually. It was specific, bespoke tailoring by the programmer for each individual algorithm. You know, staring at the circuit diagrams, trying to figure it out.
Which sounds hard, especially for complex algorithms.
Oh, incredibly hard. Frankly, trying to manually find these skips in a large algorithm, it felt like trying to untangle a giant ball of yarn in the dark. It just becomes completely unmanageable once things scale up.
And I guess that manual approach is just, it's not practical anymore, right? Quantum algorithms are getting bigger, more complex.
Exactly. They're constantly increasing in size and complexity. Plus, we're now using high-level programming languages more and more.
Right, abstracting away the details.
Which is great for productivity, but those languages can actually hide the very patterns that would allow for these skips. The structure gets buried.
So the programmer might not even see the opportunity for skipping controls anymore.
Precisely. The algorithms are just too big, too abstract for a human to reliably pick out these optimization details by hand. It doesn't scale.
Okay, so that leads us to the breakthrough. The manual way is hitting a wall.
Exactly. So what's the breakthrough here? It's the core innovation detailed in this new paper, showing how these skippable operations can be identified generically and automatically.
Automatically, by software.
Yes. The system figures it out on its own. And crucially, it works regardless of what the code is actually trying to do. It's functional intent, and it works at any level you describe the circuit, whether it's a high-level command or down to the individual gates.
So it's oblivious to functional intent at any hierarchical description level. That's powerful.
It really is. It takes the burden off the programmer.
That sounds incredibly useful. Is it perfect? Because does it always find the absolute maximum number of skips possible?
That's an astute point. The paper does acknowledge that finding the absolute optimal set of skippable operations, well, that's proven to be a computationally hard problem in itself, like NP hard.
Okay, so finding the perfect solution is tough.
Very tough. But, and this is the crucial insight, even suboptimal solutions, ones that don't find every single possible skip, can still yield major performance improvements.
Right. Better is still better, even if it's not theoretically perfect.
Exactly. We're talking about really tangible benefits here, like achieving a 50% reduction in the number of control gates in some cases.
Wow, 50% automatically. That's huge.
It's a massive win for practical quantum computing, even if it's not the absolute mathematical optimum. It's like finding a shortcut that cuts your commute time in half.
Yeah.
Maybe there's an even shorter secret path only locals know, but hey, cutting it in half is still fantastic.
Definitely fantastic. And this isn't just theory, right? You mentioned it's being used.
Correct. This approach fits perfectly into what's called a quantum program compiler. That's the software that translates the high-level code developers right into the low-level instructions the actual quantum hardware can understand.
The bridge between the human and the machine.
Exactly. And this automatic control skipping technique, it has already been integrated into the Qmod compiler, which is offered commercially by Classiq.
So it's out there, being used in the real world right now by people developing quantum algorithms.
That's right. It's not just a research paper idea. It's a practical tool.
Okay, so let's connect the dots. Why does this matter so much to, the broader picture of quantum computing, and maybe to listeners interested in the field?
Well, this method is algorithm-agnostic, meaning it works pretty much universally across different quantum algorithms, whatever their purpose.
It doesn't matter if it's for chemistry or finance or whatever.
Nope. And it works across all levels of circuit representation, from the abstract logic down to the physical gates. Because of that flexibility, it basically empowers quantum developers.
How so?
They can focus on writing clearer, high-level code. They can think about the algorithm's logic without getting totally bogged down in the weeds of gate-level optimization just to make it run.
So you can focus on the big ideas, the quantum insights.
Right. Push the boundaries of what's possible algorithmically.
And trust that the compiler is going to handle a significant chunk of the nitty-gritty optimization needed to make it efficient on real noisy hardware.
Exactly. It essentially bridges that gap we talked about. It brings that crucial hardware-level efficiency up to the level of abstract program descriptions by automatically finding and applying these control skips.
That feels like a fundamental shift. Moving from a world where maybe efficiency often meant sacrificing clarity or requiring immense manual effort to one where the compiler intelligently does more of the heavy lifting. It makes quantum algorithms not just potentially more practical, but maybe more robust, too.
I think so, yeah. It aligns perfectly with the broader goal, making quantum algorithm development more scalable, more efficient, and ultimately more practical, all without compromising on the essential efficiency needed for today's hardware.
Letting the machines handle the intricate optimization so the human innovators can focus on the next big quantum idea.
You got it.
Wow, what an incredible journey we've traced here. From, a really fundamental programming challenge, that simple if-then statement, all the way to an automatic compiler-integrated solution that genuinely makes quantum computing seem much more feasible.
It's a significant step.
We're talking about achieving real efficiency gains without all that painstaking manual effort, letting developers write clearer code, and getting significantly better performance on the hardware we have. It really feels like it opens up new possibilities.
It definitely does. And, it leaves you wondering, how might automatic optimization techniques like these control skips, how might they fundamentally change the way we even design and think about quantum algorithms in the future?
Will knowing the compiler can handle this let us explore different algorithmic structures?
Maybe. And what other sort of hidden efficiencies might be lurking in these increasingly complex quantum systems? Efficiencies just waiting to be discovered and automated.
Right. Pushing the boundaries of what's possible, not just with better hardware, but with smarter software tools.
Exactly. Allowing us to get more out of the quantum computers we have now and the ones coming tomorrow. The layers of potential optimization seem, almost endless right now.